There's a lot to cover in this lab on atmospheric humidity, so let's get on it. I assume that you have already gone through the lecture that has to do with this topic, which is essentially relative humidity, atmospheric humidity, specific humidity. And because of that, you should have a foundation. But let me just give a quick recap on the states of water. Remember, water can be a solid, a liquid, and a gas. And the term gas can be substituted for the word vapor and vice versa. Water, as a gas, is a variable gas in the atmosphere. This means exactly what it sounds like it means, which is that water can vary, in other words, change from nearly 0%, literally like no water in the air at all, to as much as 4% in the atmosphere. Its average, though, is about 0.04%, right about the same as carbon dioxide is. Now, where is water likely to be 0% in the atmosphere, and where is it likely to be 4% of the entire atmosphere? And what places is it likely to be like that? Well, if you live in Southern California, you're probably thinking of this actually opposite of what it is. When I lived in Illinois, I remember they used to say, it's too cold to snow. And I thought, too cold to snow? What does that mean? Well, too cold to snow means exactly that. That you are likely to get 0%, as in no water, bone dry air, and very, very cold air. Essentially, it's because as the air becomes colder, it becomes denser, which means the air molecules compress together, and there just literally is no place to put a water molecule. So very cold air in places like Antarctica may actually be down to 0%. And believe it or not, very warm air, because with warm air expands and that opens up space for water molecules, especially in areas where there's a lot of vegetation, like for example, in tropical rainforests like the Amazon, you may very well find the atmosphere containing 4% in total of water. There are two rules. We're going to start with the first rule, which makes sense. Rule number one. The warmer the air, the greater the amount of water vapor it can hold. Notice this is a temperature-based thing. And the colder the air, the less water vapor it can hold. Remember, water is a gas. So temperature is the key to this. With warm air, the potential capacity to hold water vapor increases, and with cold air, the potential capacity to hold water vapor decreases. It's kind of like these two glasses. Let's just assume the glass on the left-hand side is a 12-ounce glass and the glass on the right-hand side is a 16-ounce glass. What is the potential capacity of the 12-ounce glass? There's no water in it at all. But what is its potential capacity? 12 ounces, right? You could pour 12 ounces of water in there. Whereas with a 16-ounce glass, its potential capacity is bigger. It can hold more water, 16 ounces if it was full. Try to think of the atmosphere like that. Colder air is representing a smaller glass, so its capacity is diminished, potential capacity, and warmer air represents a larger glass, so its potential capacity is increased. Relative humidity, a term you probably heard before, means this. This is the ratio, that means it's expressed in a percent, between the amount of water in the vaporous state, in the gaseous state, in air of a given temperature, and the maximum amount of water vapor the air could hold at that temperature if it was saturated. Saturation just means this. This occurs when air of a given temperature is holding all of the water vapor it can possibly hold, which means the relative humidity is 100%. That means every time we say that the relative humidity is 100%, we are also saying by implication that the air is saturated. And if we say the air is saturated, we're also saying that the relative humidity is 100%, which means the air has all the water it can possibly hold within it. Take a look at these two glasses again. First, look at the left-hand side. How full is the 12-ounce glass if the blue line represents the level of water in the glass? Now look at the 16-ounce glass. How full is that glass if the blue line represents the level of water in the glass? That would be correct, 50%. This is the way we express relative humidity, by expressing a percentage, okay? Now check this out. If the glass on the left-hand side, the 12-ounce glass, is 50% full, how much water is in it? Go ahead and think about it. 6 ounces, very good, because 6 is half of 12. What about on the right-hand side, the 16-ounce glass? If that's 50% full, how much water does that have in it? And the answer is, of course, 8 ounces. If you can do that, you can do a lot of what we need to do. Relative humidity is expressed as a percentage of fullness. So remember the old adage, there's 2 ways to look at the glass, half full or half empty. This is an expression of fullness. For example, if you turn on the news and they say the relative humidity is 50%, what that means is that the proverbial atmospheric glass is half full. The air is holding half the water it could at whatever temperature it is at that moment. If they tell you that the relative humidity is 75%, what they mean is that the proverbial atmospheric glass is 3/4 of the way full. If they tell you the atmosphere is at 90% relative humidity, what they're telling you is that we are getting really close to something happening because the proverbial atmospheric glass is getting fuller and fuller. Just try to look at this like the glasses of water and you'll probably be okay. What happens when you try to pour 30 ounces of water into a 16-ounce glass? What happens? The water pours out, right? The glass reaches its capacity, which would be representative of 100% relative humidity in the air, and water comes out. What is that water that comes out? Well, if it's the atmosphere, what? Dew, clouds, rain, hail, frost, snow? We don't really know yet. But we will figure out what the actual visual manifestation is. Just not yet, but we're coming to it.